This is the first time I think I didn't make it to double digits before. Oh, there's somebody right after the class started. Now I'm at double digits. Okay. It's horrible that I feel so happy that I make it just to 10. All right. But oh well, you guys are here. That's what matters. I appreciate that. That's you guys are being smart. Any questions about the quiz? Any questions from homework? If you weren't here earlier, I unlocked the final exam solutions video. Let me be careful. The practice final exam solution video. I don't want to oversell what's available. What else was there? I think I spoke out yesterday against having another quiz. Are you guys okay with that? If we just nixed quiz 11, it was to be determined on the homework sheet. Does anyone really want quiz 11?
I mean, like, if our grade is low, then yeah, I mean, we don't know right now. So, like, is it possible, like you said, like during the weekend, then you will like figure it out, like how many points do we need? So if we need, then we will know like how many points do we need.
I need you to understand something. One quiz will not do anything for you unless it's a 0 or 106. I mean, it's right. I mean, if I give you one more quiz that basically makes each quiz worth just a little bit less than they are at the moment, does that make sense? Because then there would be 11 instead of 10, all sharing the quiz percentage I've allotted.
Oh, okay.
So, I mean, there's an argument to be made both ways, but I figure we could all use a little break from that. I figure you probably have final projects, final papers, final whatever the hell, right? Now, of course, you're still going to have to study for what the quiz would have covered, which would have probably been at least the beginning of chapter 11, right? Systems of equations, stuff like that. Okay, now, anybody questions from the quiz, questions from homework, anything? Interesting. Okay, all right, I can deal with that. So what I want to do, these things happen, Bowen. It's all right. Let me see. Am I currently? Yes. Okay. Let me turn off my background. By the way, that's a picture I took when I was up at Mission Trails. I like that picture. All right. Good job, Jeff. You put a camera towards something. All right, be quiet.
I'm not very good at it, so it's impressive all the same.
I kind of wish I had taken some photography classes because I think I do an okay job with it. All right. Here's our beautiful stuff from the other day. Oh, it's beautiful. Oh, let's see. So all right. So we have this idea. Let me see. Well, this is horrible. Let's see what I can do here. Do. By the way. It's a little better. All right. We have this idea of if I have a system of equations, let's just make a little one. Oh, good Lord, Jeff, what is that? Oh, geez. All right, sure. I think that'll work. Yeah, okay. Yeah, okay. Right, so I can put this, I can do something similar to the idea behind synthetic division, which is get the variables out of the way because all that matters are the numbers, right? It's because there's a 2 here that I would multiply this by -2, correct? Everybody who's, there we go. I see Charles now. Everybody had a camera on. I couldn't see anybody. So the way this works is I convert this into a matrix. The official name of this is Augmented Matrix because it's the matrix of coefficients that I've augmented with the answers. So each row represents a full equation then. So what I do to row 1, so I could do something, I can combine these so this would die. Oh, that would have been beautiful, Jeff. Oh man. All right, let me make one change here. I'm going to make one change. Everybody go with me. All right, let me think for a second. Make this a plus and make this 14. All right, I know that's 2 changes, but all right. I'm going to try to get more out of this problem than just this. So I'm trying to think ahead. I think that's good. Yeah, that'll be perfect, Jeff. All right. What I just did doesn't change anything about what we're going to do now. Now, somebody please help me out. Please. What would I multiply this by so I can combine it with this row and get a 0 there? Because again, what's my goal? What's my goal? What do I want to make this become? I'm with you, Kurt. Kurt's got the right idea, but help me, what's my goal? What do I want to have happen? What do I want this to look like at the end? And how do I know I'm done?
1, 0 and 0, 1.
So whatever number is here is what X is, and whatever number is here is what Y equals this. I really want that to make sense. It's so hopefully after yesterday, you guys see the utility of this. So at first it was kind of like, what is this? Some bored math person putting numbers inside of brackets and going, look at me doing shit. But then what it does is it refocuses us. It readjusts our goal. It says get ones, make zeros. Get ones, make zeros. Like I said, it makes it into a game. A fun game, but a game nonetheless. All right, I'm doing something. Hold on. Let me change this so I can, okay. All right, now. So Kurt suggested that we multiply row 1 by -2. And then I'm going to add that to row 2. Where am I going to want to put my answer?
Row 2.
Row 2, because that's where I want the 0 to show up, right? I want a 0 to show up there. So if I make that -2 and add it, I want the 0 here. So I'm going to put the answer in row 2. So if I multiply row 1 by -2, this will be -2. This will be -2. This will be -28. Now, by the way, if I multiplied equation 1 by -2, wouldn't this become -2x minus 2y equals -28? And here's the second equation, 2x plus 3y. So wouldn't I add these together, right? Isn't that exactly what this should have been? 2 minus 2 is 0. 3 minus 2 is 1. So the math in here is exactly the same as the math here. It's just that this process makes it easier to focus on what we need to do. And I got less shit to keep track of. Where am I at? Oh, 29 minus 28 is 1. All right. And then I can leave the top row alone. And now this is beautiful. This is nice. This is way nicer than what we did yesterday. Just as an example. What do I do to row 2? So I can get the last 0 I need. Where do I need? Where's my last 0 that I need?
The top right. Well, the middle, right? Yeah.
I'm with you. I'm with you. I like it. So you can say first row, second column.
Yeah,
First
that
row,
works.
second column. All right. So I want a 0 there. So of course, what do I want to do with this row? So then when I add it, these will cancel.
-1.
Multiplied by -1. So I want to do -1 row 2 plus row 1. Put the answer in row 1 because that's where I want the 0 to show up. So this will be -1 times 0 is 0. -1 times that is -1, -1. And then I do what I just said. 0 plus 1 is 1. -1 plus 1 is 0. -1 plus 14 is 13. 0, 1, 1. There we go. So the answer will be 13, 1. X is 13, Y is 1. And so if I make the problem bigger, one more variable, one more equation, the matrix gets bigger, but everything I just did, all the motivations are the same. Right, so we did an example like that yesterday. That's what I just erased here earlier. Now, let me see. Maybe I should keep this here. I don't know. No, we don't need all this. I want to, so we're going to finish out chapter 11 right now. So I'm going to show you this really cool idea. Has everybody got what they need from this? All right, I don't hear anybody objecting. I'm going to erase all this. Here it goes. Oh, what's up? How come the 0 is not multiplied by -1? It was. What's 0 times -1? I don't understand. 0 times -1 is 0. 1 times -1 is -1. 1 times -1 is -1. 0 plus 1 is 1. I mean, is that cool? Is that all right? Sorry, somebody's privately chatting to me. Okay. Yeah, you cannot. Now listen, could I come in here and say, let me add 1. Let me add 1, make that 3, add 1, make that 4, add 1, make that 30. Will that be the same equation then? Come on, you guys can do it. Come on. If I add 1 and make this 3x, add 1 and make this 4y, add 1 and make this 30. What did I just do to both sides? On this side, I added an x and a y, and on this side, I added a 1. What the hell? I'm not allowed to do that shit. And don't get me wrong, I'm sorry. Don't take it personal. Person that's chatting to me, I'm just kind of making an emphatic point. I'm not saying anything bad about you. But that's the, now listen. And again, I'm just going to call you private chatter. Private chatter, stay with me. When I write things in a different form, it's easy to forget what this actually represents. They're not just numbers. They represent variables and equations, right? Variable parts of equations. So I can't do anything to them that I wasn't able to do to this. So I can only add or subtract rows, multiply or divide individual rows by numbers. That's all I can do. I can also switch it, but all right. I think everybody's got this stuff. Oh man. So I want to remind you guys to remember that I could write this as, so this is kind of like the alternate way to write this equation. Remember this? So let me, do you see how this is basically kind of like a number thing times a variable thing equals a bunch of numbers? Stay with me now. Right? Do you guys, so number, variables, numbers, right? So how would you solve this equation? 1/3 times x equals 7.
Multiply both sides by 3.
you would multiply by the inverse of 1/3, correct? Multiply by 3.
Yes. Yes.
I love it. So if I could figure out what the inverse of this is, I could multiply both sides by that to get the answer. Let me let that sink in. I've got, now let's see, I think I've expressed, haven't I? Yes, I did. I referenced matrices with the letter A. So here's a matrix A. I'll call this matrix X equals matrix B. I think it's normally lowercase. So if I could figure out the inverse of A, I could multiply both sides by the inverse of A. Notice how I'm being very careful. If I multiply this side, I've got to multiply on this side because matrix multiplication is not commutative. Oh, shit, Jeff, why are you getting so too bad? These would cancel then, wouldn't they? I like it. So really the definition of this is the matrix that when I multiply it by A, it becomes the identity matrix. It becomes 1 basically. All right. So watch this. So I want to focus on how do we find this guy's inverse? And again, what does that mean? It just means what's the matrix that when I multiply this by it, the answer becomes 1, 0, 0, 1. Okay, now, you guys semi with me? Because again, I just had this problem up here. Why did you say to multiply by 3? Because that's the number that when I multiply it by this, it becomes 1. And then it's effectively not there really, and then I know what X is. Okay, same idea, kind of cool. So watch this. This is such a cool, all right. There's a shortcut for a 2x2, and I'm going to show you that maybe in a minute, but this is such a cool way to do this. Oh, geez. If I say the word Memorex, does anyone know what Memorex is? No? All my young people out there. All you young people. So Memorex used to be like a cassette thing that you would save stuff on. Anyway, so what could I use instead? Burning a CD? Is burning a CD even nowadays like old school? Because everything's streaming now. So what do you
Yeah, it is still old, I think.
Burning a CD is old. Shit. Too bad, Jeff. What would it be now? It would be well, now everything's downloaded.
Copying and
Recording
pasting.
a video for Instagram. So you make a memory, correct? Isn't that what a video is? It's a memory. Oh, it's so sweet. Well, someone else. Now, so this is so cool. What does that have to do with anything, Jeff? I love you guys are always like, is he teaching right now? Or is he having an episode? All right, now here we go. This is such a cool thing. If I put this matrix here, and I put the identity matrix there, and I row reduce this. What's row reducing? I haven't even used that word yet, but row reducing is when we get 1, 0, 0, 1. I really kind of want this. This is going to be like a recording device. It's going to record all the stuff I did to make this become identity so that this will now have this guy's inverse. Yeah, okay, let me see. I don't know if you guys are.
It's kind of like a roadmap of what you did with the original
been, so you
set.
know how to
Yeah.
get back.
Yeah.
Sure, I can live with that. I can work with that. All right, so let's try this out. This will be semi-easy because we've already row reduced this. So I'm going to kind of do it a little bit quickly. And of course, I've left myself 0 room. All right, Jeff, let me try this again. We can write a little bit more compactly here. I think you guys can still see that. Yes. So if I take -2 row 1 plus row 2, right, and put the answer in row 2, it's basically the same stuff we did earlier. So this will be -2, -2, but now I got to keep going. -2, 0. So now I get 0, 1, -2, 1. I'm sorry, 1. And then the first row I can leave alone. And then I'm going to multiply this row by -1 so that this will kill this. I'm just going to kind of do it. 0, -1, 2, -1. So then I'll get 1, 0, 3, -1. And then, of course, this stays the same. So here's the neat thing. If this is A, A inverse is 3, -1, -2, 1. Are the -2s above the first row significant? Oh, thank you. And somebody said burning a CD makes sense. I appreciate that. You're just trying to make me feel better. Are the -2s now? Look, no, because isn't that a 0? Isn't that a 0 right there? So what I'm writing is what I get when I do what I say that I need to do. 1 times -2 is -2, and so forth. And that's why this row, I have to do negative row 2, so I can add it to row 1 to kill him, right? And put the answer in row 1. So that's why 0 times -1 is 0. 1 times -1 is -1. -2 times -1 is 2. 1 times -1 is -1. So those are all what they would be if I did this. It's just so I don't have to rewrite the whole damn matrix just to get them to be the numbers I need for a second, right? Why do I need these numbers? Just so I can add them to kill that guy. Do I need them after I do that? No, right? So it's a little bit of a shortcut. Okay, I like it. Good question though. That actually is something people do not understand. And I'll get somebody put the same number all over. I'm like, no, I've never done that. I never put the same number everywhere because it's what I get when I do what I need to do. Now, real quick, I want to double check a couple things. All right, and I'm going to need some room. All right. Has everybody got this here? All right. I'm going to erase this. Watch this real quick. If I take this and I multiply it, I'll just do it this way because that's what we're going to do. If I multiply those two matrices based on what we just did, my answer has to be the identity matrix, correct? Because supposedly these are inverses of each other. So when I multiply them, they better come out to be 1. The matrix equivalent of 1, which is 1, 0, 0, 1. Is everybody cool with all the words I just said? And the sentences they created. Okay, so let's see. 3 minus 2, yes, 3 minus 2 is 1. 3 minus 3 is 0. -2 plus 2 is 0. -2 plus 3 is frickin' 1. So I just verified that these are inverses. They're multiplicative so they're inverses. Okay, this is a long way to go now. So that's what that method. So if I had a 3 by 3, don't write this down. How could I figure out its inverse? I would put it next to this. And then I would do everything we just did. Yes, do you guys understand? It doesn't matter how big the matrix gets. It needs to be a square matrix. What do you think square matrix means?
Equal
makes-
column and row size.
Yeah. Of course, that's what a square is, right? As long as it is wide. So as it have the same number of rows as it does columns, as long as it's a square matrix, I can find its inverse. So now you're like, okay, now I know how to find inverses of matrices, Jeff. Yeah, yay. So here's what I can use it for. I'm gonna erase this. Here it goes. Now watch this. This is cool. So if I take this equation and I multiply both sides by this. So let's see, 3, -1, -2, 1 times 1, 1, 2, 3 x, y equals. And again, with matrices, since they're not commutative, if you multiply this side of one side, you have to multiply the same side on the other. So I've got to put this here. This is a little tiny thing you got to be careful about. And what are you going to do, Jeff? You've got all this room to work with. No, I'll figure it out. We already know what happens here, right? What happens with these two?
Becomes 1.
Yes. So then my answers, whatever this is, will be the answers. And somebody remind me, what did we get? What were the answers we got? Wasn't it 13 and 1? Remember that? We just got that earlier. Remember? This is the same thing we did earlier. You guys with me? I need you to remember so that you're like, ooh, when we get the same numbers here, right? So that we got x equals 13 and y equals 1 were the answers to this. So what do I get when I do this? I think I can fit this. 42, right? 42 minus 29 is 13. Yes, yes, yes. -28 plus 29 is 1. Oh, sorry. Now, didn't that take a lot longer than the other way to do this? So on one level, I'm like, I can read your mind like, all right, that's interesting, but holy shit, that took a while. But I could actually program a computer to solve any size system of equations now, because I can tell it how to calculate matrices. That's easily algorithmable if I want to make up a word. I can create an algorithm to make it run through everything I just did. I can't do that with this shit, but I can do that if I put it in this form. Yes? All right, now, you ready? Here's the news you are really going to appreciate. And some of you guys are going to understand why I didn't say this in the first place, but I'm going to make this section extra credit. And if I would have said that in the first place, fewer of you would have paid attention. All right, and I can't really blame you. But what did I just say? I just said that I'm going to make section 11.7. I don't know why I'm so dark. I'm going to make section 11.7 extra credit. Okay. In fact, do I have it up here? Let me make that official. Yes, somebody edit this so it says extra credit. All right. Bam. I gotta make it do the day of the final. All right, now, so. Whew. So it's interesting, I want you to realize that you can find inverses of matrices. They do have a purpose for existing. A lot of what we do with matrices are in the direction of making them an algorithm in a computer program. They're very easy to program. But everything we did about Gaussian elimination, oh shit, which is just making the ones and zeros, that process actually makes it quicker by hand. For anything 3 by 3 and above. For a 2 by 2 problem, like the one we did, it actually makes it a little bit longer. It takes a poor little thing. But the minute it's 3 and up, the matrix wins hands down. Okay, so I've just changed 11.7 to say extra credit, and I've taken the due date off. So it's due by the day of the final. All right, there you go. So what we're gonna do, I'm sorry.
So it was, the method was the only way to know the inverse of matrices.
Yeah, this I've already erased it, but where you
Yeah.
put the matrix and then you put 1, 0, 0, 1, depending on how big the matrix is, right? So it will work for any size matrix as long as it's square, like 4 in the row, 4 columns, right? Then that process of putting the identity matrix next to it and doing Gaussian elimination will always find the inverse. Yeah. Now there is a shortcut for little 2 by 2s,
Yeah,
and I can't remember if it tells you in the book or not.
not sure. I haven't checked it.
I don't know. Maybe I'll tell you. Let me see. Here, I'll show you.
Only a 2 by 2.
Yeah, it only works for 2 by 2s. There's no shortcut for bigger ones. So if I have a 2 by 2 matrix, oh, let's see if I even remember it, Jeff.
Butter.
Everybody all right?
Broccoli.
Somebody say broccoli. Okay, I can't help with the grocery list. Okay. So to find this guy's inverse, it'll be 1 over, get out of there, AD minus BC times, now let's see, this is what I always forget, negative AC B negative D. Is that right, Jeff? Or did I get that backwards? I might have got that backwards. Let me look at it. Let me think about it. Yeah, those switch. Oh, yeah, I got it backwards. All right. It's been a while since I did this little shortcut. It should be DA negative B negative C. All right. Holy shit. So now watch real quick. So these switch places and these become opposite signs. So look here. Here's matrix A, B, C, D. What is AD 3 minus BC 2? That's 1. That's 1. So it'll be 1 times. Now, if I just take 3 and 1 and switch them, see how 3 and 1 switched? AD switches. 3, 1 switches, and then I make these opposite signs, bam. Bam. All right. So but that shortcut only works for 2 by 2. There is no equivalent shortcut. Well, there sort of is. Yeah, there is a shortcut, but it doesn't really make it that much shorter, but yeah, anyway, I'm going to leave it at that.
Thank you.
You're welcome. All right, so what I want to focus the rest of today on is a little bit of a step into chapter 12. And that's the one where I made the homework only from the review section. So it's a smaller collection of homework, but it spans all of these different ideas. And what it's going to be talking about is ellipses, hyperbolas, and parabolas, right? The different kind of bolas and the ellipse. I like it. So, and these things are called conic sections, which is really weird. Stay with me now. And circles are a part of this too. Watch this. This is kind of cool. Let's see if I can draw this anywhere near well. I could probably find a picture that would be better. Yeah, let me find a picture. Yeah, I'm going to screw this up. I really want you guys to see real quick why we call them conic sections. Let me find a better illustration of that. Oh, beautiful. That's beautiful. Let me see. All right, this is perfect. Okay, here we go. Where'd you guys go? There you are. Oh shit, there it is. All right. So I have a cone and then another cone below it. So I have like 2 ice cream cones that some bored kid slurped all the ice cream out of and put one cone on top of the other cone. Do you guys see that right here? And if I slice it like this, I get a parabola. See that parabola? If I slice it straight across, I get a circle. If I want a bigger circle, just take a slice further down or further up, right? If I slice it at an angle through the center, not through the center, but through both sides, I get an ellipse. An ellipse is just a circle that somebody sat on, right? It's squished. It's longer in one direction than the other. And then you get, here's the hyperbola. Hyperbola, I always like to think of a hyperbola as an ellipse where it turned away from itself. Yeah, so here's an ellipse. And if they're like, I'm not going to talk to you anymore. I'm not going to talk to you anymore. And they turn around, that's a hyperbola. All right. So I don't know. All right. That's the therapy version of conic sections. I don't. You got to make the relationship more elliptical instead of hyperbolic. All right. Did we do 11.8? No, 11.8 was not a part of our, what do you call it? Journey. If you look at the homework sheet, it wasn't a part of our curriculum in the first place. Now, let me see, where am I at again? Where are you guys? There you are. So what we're going to talk about in chapter 12 are the equations for each of these things. So let me see if you guys remember, and you should, what the equation of a circle is. And that's going to kind of get us started. So I kind of want to do this in this order: circles, ellipses, hyperbolas, and then parabolas at the end. Because believe it or not, parabolas are more complicated than we kind of realize. Everything else is actually nowhere near as complicated, to be honest. All right, here we go. Can somebody give me the equation of a circle of radius 4? Does anyone remember?
X squared plus
Yes.
y squared
Yes.
equals 4 squared.
Yes. Now, real quick, let me do this. This is interesting. I don't know if you guys, does anyone remember this? Right? And if I wanted to move it, I can make this x minus 1. So it move over 1, y plus 3. So it move down 3. So I can move the center if I wanted to. So this is centered at 0, 0 with a radius of 4, because that's 4 squared. Now, could I do this if I wanted to? Of course I can, right? So I now watch, just go with me, This is so cool. What's the biggest x can be looking at this equation? What's the biggest x can be and keep everything real?
1,
Say again.
1,
No. It can be bigger than 1.
4,
4, yeah. So think about it. To figure out what the biggest x can be, can't you at the same time figure out what the smallest y can be? Wouldn't that answer that question? And actually y squared. What's the smallest that y squared could be?
Negative 4. Oh, 0.
Oh, that would make y squared 16, which is big. What's the smallest y
Okay,
squared
yeah.
could be? 0. I really want this to make sense. If x is 4, isn't this 1 already? Do you want to add anything to it? If x is 4, do you want this to be anything? Isn't this 1 already? I really want you guys with me on this. Yeah, if x is 4, that's 1 already. I don't want to add shit to it, so that should be 0. And of course, what about y? What's the biggest y can be? It's symmetric, right? It's symmetric, so it's the same. It's still 4. So that's why this is a circle, because it doesn't treat the X and Y direction differently. It's 4 all different directions. 4, 4, 4, 4, and you get a circle. Ah! All right. I know it looks like an ellipse, leave me alone. So this is a circle. That's amazing, right? And we normally write it like we had at the beginning, just because we're not weird. What change would you make based on what I just said that would make this into an ellipse?
Change either side of denominator.
Yes, make one of these denominators different, because the defining property of an ellipse, well, one aspect of an ellipse is that it has a different length in one direction than the other. If they were the same length, it would be a circle. So doesn't it make sense? For example, what if I make this x squared over 16 plus y squared over 9 equals 1? What's the biggest x could be now? It's the same reasoning, right? What's the biggest x could be? You can do it. When is this 1? So it doesn't need any y. When x is 4.
4.
So x still goes out to 4. But now what's the biggest y can be?
3.
3. And let me be careful, it's 3 and -3 because it's squared. Is that cool? That's why I'm going in both directions. So now it only goes up to 3 and -3 in the y, but it goes up to 4 and -4 in the x. So that's, of course, what makes it elliptical. Isn't that too nice to believe? No? Okay, it's all right. If you don't agree with me, you don't have to say yes. It's okay. That really is too nice to believe, though. It has to be. So a circle can be written like this because these are the same. Can I do something like that for this? Not really. If I multiply by the LCD, I'm going to get numbers out here. So circle is normally written like that because it can be. But this is kind of like a more interesting form for it because it helps us explain this. So let's try something out. Let me see. I'm going to erase all this. You ready? Here we go. Oh, I should have. Here, before I erase this. And I've already erased you, so I'll just do this. No, Jeff, that's positive. There you go, buddy. Just to get some terminology down here. This is the major axis. This is the minor axis. That kind of makes sense. Is the major axis always going to be on the x-axis? So this is the major axis. This is the minor axis of the ellipse. Will the major axis always be on the x-axis?
No.
Of course not, because what if I had turned these around? Then it would have been longer in the y direction, correct?
Could it be diagonal?
Oh, yes. Didn't I show you an equation that led to a diagonal ellipse? Wasn't it a little bit funkadelic? In fact, I believe it was in polar form, if I remember correctly. So what would that look like in rectangular form? Not too pretty. I like it. And just to throw this out there, you can use matrices to transform any rectangular function, to transform it by rotating it by any degree you want to. Isn't that interesting sounding? Yeah, too bad we're not going to talk about that. That's a little bit beyond us, but that is another use of matrices. I think I said that before, that they're like transformations on something. So this, just this piece here, this is called the semi-major axis. Oh God, Jeff, can you spell? No. Oh, semi-major axis. Not surprisingly, really. So how long will the semi-major axis be? It's going to be based on what this thing is when I take a square root, right? When I take a square root of this, That's going to be what the semi-minor axis, how long it's going to be in both directions. All right, maybe. So, and the nice thing is I do have a handout about this. Of course I do. Has everything I'm talking about explained. So let me make up another problem. Oh, I always forget to say this. I sort of implied it when I discussed the circle thing, but I really want you guys to understand why. Do you guys understand if I say a circle and an ellipse are contained, whereas a hyperbola is not contained? Would you guys agree with me that that's one way you could reference that? I just fixed it right now. Oh, I see. Okay. So a circle and an ellipse. Pretend that's a circle and really pretend that's an ellipse. They're contained, whereas a hyperbola is not. So here's one reason why. If I have two positive numbers that add to be something, can X be as big as it wants to be? Can X be 5?
No.
No, because I would have to subtract something from 25, and this is going to be positive. Contained, right? Contained. Okay, maybe. And the same thing's going to happen here. X, like we said, X the biggest it could be is 4. It's contained. So that's why the graph is contained, because you can see in the equation, the variables are contained. They have a max and a min. Okay, I'm making a big deal out of that, I know. All right, so that's going to come back here in a minute. But here, what do you guys think about this? You could do it, Jeff. Yeah, sure. Okay. Let's see. And then we could do. Sure, I like it. Sure, that's fine. We won't make this too freaky. All right. All right. Is this in the right form to analyze? How can you tell this is definitely not a circle?
Because the coefficient is different.
Coefficients are different. So the leftover underneath is going to be different when I do what I got to do. So the official form of an ellipse is x squared over a squared plus y squared over b squared equals 1. If I get it in that form, then I can tell what the semi-major and semi-minor axes are. So of course, what do I have to do here? Something very simple. I just have to
Divide by LCD.
divide by 30. No, just divide by 36. I just need a 1 here. That's all I care about. Whatever else happens, happens. I need a 1 here. There's only one way to make that happen. So then I hope everything else works out. Okay. So of course it does, right? What does this become? This is going to be x squared over
1/4.
4. No, careful, just x squared over 4, right?
Yeah.
Yeah, thank God. Although it could be over 1/4, but we're not doing that yet. Plus, I would put y squared over 1 just to remind myself what's going on. So what is A then?
2,
2. And of course, B is
1.
1. I like it. So now I know how to graph this thing. Let's find out if that's true. Just take a second and graph this ellipse. I know it's an ellipse because it's a plus, and these numbers are different. So it's not going to be the same in both directions. It's going to be different.
So those are just the two radiuses?
Yeah, be careful. There's not really a radius with ellipses, right? Because a radius is a set distance from a center, and there's no such thing in an ellipse. There are ideas related to that, but it would be constantly changing. As I move through my angles, the radius would be changing, correct? Does that make sense? Because of course it gets closer. So think of this as major axis, minor axis, or even less terminology ridden. How far do I go out in the x direction?
2.
Yeah, I go 2 out in the x direction. So 2, 2. And how far out do I go in the y direction?
1.
1. So 1 this way, 1 that way, and then there's my ellipse. Oh, Jeff. All right, there. Now I might as well talk about, all right, how do I want to say this? There is a point. All right, I don't know. Does anyone know much about astronomy? Real quick. You've got the sun. I'm the sun. All right. And you got the earth going around the sun. Is the sun in the middle? Oh, that's funny, Bowen. I like that. Did I say astrology? I hope I didn't. Astronomy. I might have said I said astrology.
You said astronomy.
Astronomy. Okay. Yeah, I don't know. Somebody's telling me they're a Virgo. Astronomy. As the earth goes around the sun, is the sun in the center of the earth's orbit?
It orbits at an ellipse
It does.
or an oval.
Yes. And not an extensive, not like a really obvious one, but I'm going to kind of overdo it a little bit. The sun is at one focus. So in every ellipse, there are 2 foci. Okay. A circle has 1 focus, and that's the center. An ellipse has 2 foci. So it'll be somewhere here and somewhere there. We're going to actually find out exactly where they are. And the way we do that is kind of weird. All right. Everything's going to become much easier to memorize when I get hyperbolas up here. But to find the focus, we call the focus length C. Does that make sense? A, B, C. And the nice thing is, so this will be negative C here. The formula is C squared equals, now this is kind of funny because it depends on, it's got to be the bigger one here. Hopefully you understand what I'm saying. So if this was turned around, I might turn these around. All right. I'm going to have to come back and show you the proof of that later because I've actually forgotten how to prove that, to be honest. I didn't look that up. So for example, this focus would be C squared equals 4 minus 1. So that's A squared, that's B squared, right? So 4 minus 1. So C is the square root of 3, which I think is 1.75. Is that right? Or is it 5.7? I always get that mixed up. 1.75 probably, because 1.57 would be pi divided by 2, which I would remember. Can somebody double check me? Square root of 3?
And that's plus or minus?
Plus or minus, exactly. Square root of 3 is what now? Somebody got that? Is it 1.75 something?
1.7.
I lost you. 1.75. Okay. So 1 point. So it's roughly right where I put it. Yay, Jeff. Go, Jeff. So it'll be 1.75 and negative 1.75. I like it. So as these two numbers get closer to each other, the foci get closer to the center, because if A equaled B, what would this be? If A equaled B, this of course would be what?
0.
0. And that would be a circle then, right? So if I get the foci closer and closer together, I'm making this more and more circular. If I push the foci out more and more, I'm making this more oval. I'm making this more
I'm
elliptical.
sorry, what is foci?
So in astronomy, for example, the focus. All right, let me actually do it this way. So here's the real definition of an ellipse. I have not told you the real definition of an ellipse yet. And I actually might want to show you a picture because I'm going to screw it up if I try to draw it. But it's basically, there's a neat thing. If you put two, I'm going to try to draw it apparently. If I put two nails down in a board, and then I put a piece of string kind of loose between them, right? And I put my pencil here and I pull the string taut and I kind of go around letting the string kind of guide me. So I'm pushing against the string, but the string is keeping me in. Let me show you a picture because that's horrible what I just did. This looks like, I don't know what that is. I don't know. All right, so let me show you a picture. This is really, the funny thing is there is a mathematical result from the definition of an ellipse like this. Let me show you. Hold on. All right, Jeff, you could find it. Ellipse. Let's see if it'll show me. No. All right, let me do this. Draw ellipse. There it is. All right. Yeah. Okay. This'll work, I guess. Yeah. Okay. Some of these are better than others, but we'll see. What do you guys think? See here? Here's the string. They're saying they have a pin here and here. And if I put the pencil in there so the string is tight and I start to just trace, keeping the string tight. Are you with me? So of course, the further I get away from this pin, the more it's going to pull me in. Okay, and if you do that, you will trace out an ellipse. So the foci are actually what makes the ellipse look the way it does. If they're closer to each other, it's more circular. If they're further apart from each other, it's going to be much more pronounced, kind of cigar shaped, right? Classic UFO. And of course, they could go this way also. So that's one thing I didn't say, is that foci always sit on the major axis.
So foci is a pin in this case.
Yes, if you want to consider it, there's a few different ways to think of foci, but this is a really beautiful one because it has a couple of their ideas. So foci are locations from which points on the ellipse can only get so far. So it's kind of like the distance. So let's make this more mathematical. The distance from this pin to a point. Let me see how to say this. The distance from this pin to a point added to this pin to that point is a constant. Right? Because the string is only so long. So doesn't this distance plus this distance have to equal a constant, correct? I love you guys. I love you guys. If you really wanted me to, I wasn't planning on doing this, but I can actually show you the full proof mathematically. If you select locations for the pins, I can show you how the math gets you to the equation of an ellipse. It's very exciting. Or maybe I can write it down and put it up on Canvas so you can look at it if you want to. We'll do it that way instead. All right, all right, there's a lot of really cool shit with this. I am obviously trying to truncate my lecture down a bit because we only have so much time left in this class. So I feel a little bit like I'm shortchanging you, but I also don't want to overload you at the end. So it's a weird balancing act I'm doing. Where am I at? 1 point. Oh, okay. All right. Okay. Here we go. Let me come back up here. Pop. So the way that an ellipse is contained is because it's two squared pieces adding to be something. And that makes it contained because then each variable can't, they're going to have a max and a min. So if I have so that's going to create a circle or an ellipse. If I have two squared things equaling something where their coefficients can either be equal or not, that's going to lead to a contained object. I really want this to make sense. Why do these graphs make sense? Because this is a positive plus a positive equals a constant. Therefore, each one can only get so big. Contained. So if I want to do a graph like this, that's not contained. How big can y get? Infinitely big. How big can x get? Infinitely big. So let me ask you this. If I tell you, so x squared minus y squared equals 4, let's say. Can x be 7?
Yes.
Hell yeah. Right? Can x be 873 million?
Yes.
Yes. All day long. So how do I say this? So I mean, I can imagine. So if I kind of ignore the squares, so if I have a positive number minus a positive number equals 4, well, this could be 9 and 5, 10 and 6, 11 and 7, 83 and 79, 8 million and 4, 8 million. I mean, sky's the limit, correct? Now, in the other way, there is a closest approach. Does that make sense? There's a place where they get the closest they're going to get. So there's kind of like an excluded middle here. So A and B, what's the closest that they can get? I don't want to say this. Well, 4, right? So if there's no way in hell to make the number A be closer to B than 4, because the definition of this equation is the difference is 4. They can't be 2 apart, for example. I don't know if you guys are with me or not. So all of these observations about the equation make sense as to why it might end up looking like this. Also notice that this is sort of like the opposite of an ellipse. Like I was trying to say earlier. An ellipse is plus, so hyperbola being minus kind of makes sense. Okay, now let's focus on this. I'm going to pull this up here.
So like instead of an asymptote, they have a whole area where it cannot be exactly.
Yeah, and that, yes, there's that excluded part in the middle. Exactly. So I like that. It's not quite an asymptote. It's a whole region it can't be in. So let's look at this guy. X squared minus y squared equals 4. Let's do the same thing we did before, right? X squared over 4 minus y squared over 4 equals 1. Okay, now. So let's see now, watch this. If y is 0, what is x? You could do it. It would have been easier up here, but sorry.
2
2 or
minus 2.
-2. If x is 0, what's y?
0. No.
Nope. So what happens if x is 0? What something catastrophic happens,
I.
right? You get negative y squared equals 4. If I multiply that up, you guys with me out there? Is that possible?
Imaginary.
Yeah. Do you want to bring imaginary into play here? No, you do not. Trust me. So yeah, we're keeping it real, right? We don't want imaginary stuff. So there cannot be a y-intercept. There's only x-intercepts. Yeah, I like it. So that's our closest approach. Right now, so the positive variable is going to tell you which axis they sit on. Okay. Now here's what's kind of cool. Let me see if I can get this understood. The curvature of this thing will be related to the curvature of the ellipse if that was a plus. So watch this. If that was a plus, would I just go up to, down to, and then I could just make, then it would actually be a circle then, wouldn't it? Right? Right? Okay. Let me see. What else how else do I want to say this? Let me think. Well, all right, let me do this. Well, I'm trying to remember how this works because I haven't had time to look anything up. The way we normally do this is we can draw. So this would be, I'm not going to put like a point there, but that's where the circle would be if that was a plus, correct? That's where the points for the circle would be. If I make a little box. Okay. So this is kind of cool. And this is why when he said asymptote, I was like, wait a minute. What does he mean? Because there comes an asymptote into this thing. The asymptote is the line through the corner I just made. So now I can draw, so here, this has got to follow that line, and this has got to follow that line. This has got to follow that line, and this has got to follow that line. Now, the proof of that, let me see. If I kind of get lost here in the middle, because there's a couple of weird little steps, but let's see if I can remember this. So it'll be x squared over a squared minus y squared over b squared. This is a general hyperbola. A and b could be equal to each other. The main thing about a hyperbola is that's a minus. That could be a y. If that was a y and that was an x, it would have been up here and down there. So whichever variable is positive, that's the axis it sits on. Does that make sense? Isn't that sitting on the x-axis? Not touching the y-axis because the x is positive. If I would have turned these around, it would have been up here and down there. All right.
So and ask if you could repeat that.
Again, sorry. Oh, can you repeat that? Oh, geez. Whichever variable is positive. Do you see how the x piece is positive and the y piece is negative? Whichever variable term is positive, that's where the hyperbola sits. It sits, it hits the x-axis. I call it sitting on the x-axis. If I would have turned these around, what would this equation be graphed as? See how I just turned those around? The y and the x? Creepy fillet dude. All right, whatever gets to. Then it would have been here and here. Oh, I see what you mean. I agree. Okay, great. Thanks. Thanks. I hate that. All right. I'll never look at hyperbolas the same way. Okay. All right, let's see if I can do this. So, all right, this gets exceptionally weird. So I'm not sure if I'm going to be able to remember all the parts of this. Let me see. Hold on. Let me see if I can't trace out something that looks roughly correct. There's something else here. All right. All right. I'm not even going to try. I'll show you the proof tomorrow, but there's a couple steps I always forget if I don't look them up. But you can kind of see this is headed in this direction. The asymptote is going to always be plus or minus b over ax. So I got those the wrong way around to begin with, but anyway, I got to look that up. Okay. So let me do this because that's a lot that I just threw on in your brain. Let me show you the handout that I've got up on Canvas for this stuff. Okay, let's see. Here we go. So if you go to unit, there's a new unit 12 now. Conic sections. So this is not the prettiest thing. Don't worry about parabolas. We haven't talked about parabolas yet. But here's ellipses. Okay. And there's an example one. Okay. And then here's hyperbolas. And look at their foci. And why does this make sense? Hold on. In this picture, where should the focus be? I always think about the focus is like somebody is have you ever seen that guy, that old photo of the guy with a cannonball getting shot at his stomach? And this, don't worry, this is not torture porn or something. This is just a guy at a circus, and this is what he does. He gets shot in the belly with a cannonball. So I was thinking about the focus as the cannonball. If you saw a cannonball coming towards your stomach, what would you do? Wouldn't you kind of like bend? Wouldn't you kind of like double over? Wouldn't you kind of like, whoa? So that's what I think of. So for an ellipse, it makes sense that the foci are in here, because if they're going that way, isn't that where this guy's going to double over? Boom. So where would the foci be here? Wouldn't they be out here? And that is why the equation for the foci for a hyperbola is c squared equals a squared plus b squared. It's going to be further out than either a or b. Ellipse is a squared minus b squared, so that it's inside. Okay, maybe. Okay, so tomorrow I will be ready to show you the proof of this. We will talk about parabolas, and then we'll probably get into, well, we'll see. We'll see how we're feeling tomorrow. Yeah, that's I think is plenty for tonight. So, okay.
Thank you.
So let me know if you have any questions. Otherwise, you are free to go, and I'll see you all tomorrow.
Have a good night.
You too. All right. I don't see any questions. Sorry for earlier. Oh, that's fine. Don't worry. Don't worry. I thought it was a grocery list because I thought I heard broccoli or something. You're fine. All right. I'll see you guys.